A loaded freight train cannot safely descend a grade of 4.5%. That is roughly 230 feet of drop for every mile of track, and it is about double what North American railways of that era treated as a workable ruling grade. Yet in 1884, on the western slope of Kicking Horse Pass in the Rocky Mountains, the Canadian Pacific Railway laid exactly that. Engineers knew what it meant. Brakes on wooden-framed cars, hand-set and limited by how fast cast iron can shed heat, would be asked to hold a moving train against gravity for miles. Once those shoes glow, the friction that stops a train starts working against you. The company built it anyway, and then spent 25 years living with the consequences before it found a way out that did not involve moving a single mountain. The company itself was young. Canadian Pacific was incorporated in 1881, chartered to push a continuous line of rail across the width of a country that had promised British Columbia a transcontinental connection as a condition of joining Confederation. That promise was political first and physical second, which is the source of almost everything difficult that followed. A railway built to a deadline cannot wait for the cheapest alignment or the gentlest one. It has to take the route it can finish. On November 7th, 1885, the last spike went in at Craigelachie, British Columbia, and the line was declared complete. Completion and operability are not the same thing, and the west side of Kicking Horse Pass was the proof. Here is the physical constraint that shaped the entire story. The Kicking Horse River leaves the Continental Divide by dropping fast into a narrow valley. Water can do that. Steel cannot. A railway can only climb or descend at the rate its wheels can hold friction and its brakes can shed heat, which in practical terms of the 1880s meant a target closer to 2%. To hold that limit, the descending track needed far more horizontal distance than the valley offered. The original survey answer was a long summit tunnel that would have brought that distance underground. It was expensive, slow, and it sat in the way of a deadline. So the tunnel was shelved, and the railway did the arithmetic differently. It accepted the mountain's gradient and tried to manage the risk with operating rules instead of excavation. The result was called the Big Hill, and it was a temporary line that lasted a quarter of a century. Trains descending it ran under speed limits in the single digits, measured in miles per hour. 3 safety switches were installed along the descent, and the crucial design choice is that they were set by default to divert a train off the main line and onto an uphill runaway spur. A crew had to prove control before a switchman would let them continue. Gravity was treated as the normal condition, and the train as the exception that had to be demonstrated. Going the other way, a single locomotive was not enough. Heavy trains needed multiple engines working the grade, with helper locomotives stationed permanently at the bottom for no purpose other than this one hill. Runaways happened anyway, including during construction. Every ton the railway hauled west paid a tax in fuel, crews, time, and accepted danger. The turning point came from a different pressure than safety. By the early 1900s, traffic volumes were rising, and the Big Hill had become the throughput ceiling for the entire Western Line. You can tolerate a dangerous hill on a railway that runs a few trains a day. You cannot tolerate a hill that caps how much freight a continental system can move. The constraint stopped being a matter of risk and became a matter of revenue. CPR's senior engineer, John Edward Schwitzer, reframed the problem. The railway had been trying to fight a vertical drop. Schwitzer treated it as a shortage of horizontal distance and asked where more distance could be found in a valley that plainly had none left. His answer was to stop looking along the valley and start looking inside the rock walls on either side of it. The mechanism is simple enough to draw and strange enough to sit with. A grade is a ratio, vertical drop divided by track length. The drop through Kicking Horse Pass was fixed by geology. The only variable left was length. So the new line was routed into Cathedral Mountain, curved through a complete circle inside the rock, and emerged lower down and facing the way it came. Then it crossed the valley and did the same thing again inside Mount Ogden. 2 spiral tunnels, each one a loop of track that goes nowhere horizontally and does all its work vertically. The tunnel does not shorten the climb. It stores it, wrapping the descent around a fixed point until the numbers come out. The additional mileage, roughly 4 miles of track added to the route, cut the ruling grade from about 4.5% to about 2.2%. The descent was halved by being made longer. The line opened in 1909, and a train on it now crosses the same stretch of valley 3 times at 3 different elevations. Nothing about that was free. The tunnels were driven by hand drilling and explosives through hard rock, on a project that published accounts generally describe as employing around 1,000 men and costing on the order of $1.5 million of the period's money. Treat both figures as commonly cited estimates rather than settled numbers. The engineering trade was explicit and permanent. The railway paid for reduced risk with extra distance, and it pays for that distance on every trip, in every year since, in fuel burned and running time spent. That is the pattern worth noticing. Kicking Horse was not solved by a stronger machine or a better brake. It was solved by accepting a longer route forever. The spiral tunnels are also not the whole answer, and it is worth being precise about their limits. A 2.2% grade is workable, not easy. Helper locomotives and heavy braking discipline remained part of operations, and the Rockies were only the first mountain problem. Further west, the Selkirk Mountains at Rogers Pass produced a different threat: snow. Avalanche paths crossed the line, and snow sheds built to bridge them proved to be partial protection at best, because a shed protects the track it covers and nothing on either side of it. In March 1910, an avalanche struck a crew, clearing an earlier slide at Rogers Pass, killing a group of workers usually numbered at 58, though published counts vary. That disaster pushed CPR to abandon the surface crossing and drive the Connaught Tunnel beneath the pass, which opened in 1916. One further caution: the human cost of the mountain construction as a whole, particularly among the Chinese laborers who worked the British Columbia sections, is documented incompletely, and historians' estimates differ. That uncertainty is real, and it should not be smoothed over. Today, the crossing is still working infrastructure, not a monument. The spiral tunnels carry freight through Kicking Horse Pass every day on the alignment Schwitzer drew. At Rogers Pass, the Mount McDonald Tunnel opened in 1988 at about 14.7 kilometers, cutting the grade further and taking pressure off the older Connaught bore. 8 decades apart, both tunnels answer the same question the Big Hill asked: where do you find distance when the map refuses to give you any? The railway, incorporated in 1881, has since become part of Canadian Pacific Kansas City. The name adopted in 2023 after the corporate structure changed, and it remains one of Canada's 2 principal freight railways alongside Canadian National. Passengers can still see the route. Via Rail's transcontinental train, the Canadian runs between Toronto and Vancouver's Pacific Central Station. The lesson the Rockies enforced is narrow and durable. Canadian Pacific tried to beat a gradient with operating rules, and for 25 years, those rules held mostly by demanding constant vigilance from crews who had no margin to spare. What finally worked was giving up on the short route and buying length inside the mountain itself. Every train that loops through Cathedral Mountain today is running on the same admission. The terrain set the terms, and the engineering that lasted was the engineering that agreed to them. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.